Okay, this is second attempt to finish this final run through of the June 2023 Physics Edexcel International A-Level for the preparation of students for Unit 6, the practical exam, the practical skills exam used in Year 13, which is the final exam of the series for this summer. Okay, so we went through question 1 in the first video and I showed you the beginning question 2. So straight into question 2, we'd looked at the safety precautions, so you need to go back to the original video if you want to look at this. Part 2, Part B, a student planned to test whether beta particles are absorbed by aluminium according to the relationship C equals C naught e to the minus mu x, which is the half thickness value. Is one of the core practicals. They usually use gamma radiation, so this is a variation on that theme for the core practical. So it tells you C is the count rate when the thickness of the aluminium sheet is X. Okay, so C depends on X. C naught is the count rate with no aluminium sheet, so that's the maximum count rate. And mu is a constant which can be determined by taking log graphs. So it says explain why a graph of ln C, natural log of C, against X could be used to test the validity of the relationship. Well, if you take natural logs, you change the equation to this. You need to make sure you know how to take logs. The natural log of C will equal the natural log of C naught minus mu x. Well, that's in the form of y equals mx plus c, yeah, where the C naught would be the y-intercept and it's going to go downwards, yeah, when you plot it. So the gradient is negative because obviously the values go down each time you put an x thickness of aluminium in there. The value of the count rate will decrease, okay? So taking natural logs should give you a straight line graph, so that will test the validity. If you do get a straight line graph, then it shows that the relationship could be right, where the gradient will be given by, would give you the value of minus mu. Okay, it'll be a negative gradient, remember, and the intercept, as I explained, will be the natural log of the original value without any aluminium in the way. Okay, so log graphs are definitely used in this exam. Then it says you have to devise a plan. So again, if English is not your first language, this is a 6-mark question. You need to write out a whole plan, and I put the mark scheme up. So here is the plan. Yeah. So it says measure the thickness of X with a micrometer to be accurate. So a micrometer can measure with a resolution of plus or minus a resolution of 0.01 millimeters. So you want the thickness accurately, so you get a good graph. Record the count rate, it says, over a long period of time. In other words, do it for like, I don't know, 60 seconds or whatever. That's what they mean by a long period of time. They don't mean do it very quickly, because obviously the count rate of any radioactive material is spontaneous and it's random, so you don't know when you're going to get it, so you need a long period of time to get an accurate count rate. Then obtain the count rate for at least 5 different values of thickness X, yeah, so you get 5 points on your graph as a minimum, yeah, and then keep the distance between the source and the detector constant. So this is like showing that you know the controlled variable aspect of planning an experiment. Okay, so you know the independent variable, you know the dependent variable, and you know the controlled variable, and you know what to measure. So this is that you need to know your apparatus you're using, the measuring instruments you're using, how to get reliable data, long period of time. So this is testing you on quite a few practical skills, and then it gives you 2 options to get the 5th and 6th marks for. Record the thickness in several places and calculate a mean. So obviously the aluminium that absorber may not be of uniform thickness, so this is a way of again getting accurate data. And another way you could get the accuracy marks up is check and record for 0 error. Yeah, for example, on the micrometer might have a 0 error on it, especially if it's been badly used before. It may not have started on 0, so it's always a good idea to check that. And it says also, and I think this is important, record the background count rate and subtract it from your count rate, because obviously some of the radiation will not be due to the beta source. And I think this is the most important point to make if you're doing any radioactivity experiments. Okay, so that's how you get, there's 7 ways of getting the 6 marks, basically, in simple terms. Okay, so that's question 2 done, that's 10 marks done. And then we're going on to question 3. Okay, so question 3 is about bending, investigating the bending of a flexible wooden beam. Okay, so you put the weights in the middle. Yeah, so the load or the weights are put here, and the center of the beam was displaced downwards, so it's a flexible beam, by a distance d is shown. So it starts off here, flat, the dotted line there is the flat position, and then at the end of putting the load on, it goes down by this much. So you've got to determine this value. Describe an accurate method to determine a single value of d using a 15 centimeter ruler. Okay, you should include any additional apparatus you may need. So we're going to have a look at the mark scheme. So just to save time writing it out, the first point, this is 3A. You can also see the part of 3B as well. So record initial and final positions of the center of the beam where the load is, and subtract to give D. So you need to record the initial and final positions of the beam. Okay, well obviously the initial position of the beam, if you look at it, is going to be the same here. So you could do the bottom of the beam, so you could actually measure this distance here, couldn't you? That's going to be fixed. And then at the end, you could also measure this distance. So say D1 and D2, depending on the load. So each time you do that, so you could put your ruler there. So the first point is you've got to make sure you do the initial and the final positions of the center of the beam and subtract. So they want you to get that, but you could do what I said. So that obviously the initial position will be the same along the beam as long as the beam is perfectly horizontal. But you must say and subtract one from the other to get the values. So that's the first mark. And then you can get, so this one is compulsory, and then you can get 2 more from these 3 marks. Use a set square to ensure the 50 centimeter ruler is vertical. So you don't just say use a set square. You've got to explain why you're doing it and what for. Clamp the ruler in position vertically, so make sure it's vertical, okay? And read the perpendicular to the scale. And how can you do that? By saying that you could say use the set square to ensure that you're reading perpendicular to the scale to avoid parallax errors, okay? And then here's another way you could say ensure the ruler is close to the beam. So don't, obviously, that's just common sense. So these are the ways of getting the marks. And while I've got this on the video, I'll show you the data for 3B. You may want to go back to and stop the video when you're looking at your 3B section. Okay, so that's 3A. 3B is then the student varied the distance L between the supports. So change the distance between the supports in the question. So we can have a look at that if you need to. And the student used vernier calipers to measure the distance D for a constant load. Okay. She recorded the data. Now you don't need to talk anything else about the practical. This is now the investigation, and they want you to plot a graph of it. So it's now they're using not natural logs, but log to the base 10. Okay, so that's log, whereas natural log is ln. And whenever you put a log of something, so they want you to plot a graph of log d, so there's log of this value against a log of the L value. And if they've got 3 significant figures here, then you need to put your data to the same number of significant figures or decimal places. We'll have a look and see what they've given you there. So you're going to put the graph on the grid they've given you, and you use these additional values to work out the log of L in meters, which you always must put the brackets for this exam around the thing that you're doing it, because you could also take the log of L in centimeters, but you've got to make sure you've written that you're taking the log exactly of this in brackets and the log of D in brackets. If you don't put the brackets on your graph, you lose you'll lose the mark for the labeling. Okay, so you need to put these on the graphs exactly as I've written it in this table. Okay, so let's look at the values. So how have they put the values that we just looked at? So when we're looking at the values, you will see that they want you to have the values of log L here to 3 decimal places. So here they had 3 decimal places, so they want you to use 3 decimal places. Okay, so obviously two of these are 0. So that's the level of consistently 3 decimal places there, 3 decimal places here, and the same for log D. They got more than 3 decimal places here, but obviously when you take the log D, this is 4, if you like, this is 3 significant figures or less. They want you to have consistency in the number of decimal places, and I think that's the best way of doing it. They would accept 2 decimal places. Okay, so then you have to label your axes as I mentioned, exactly as I've shown you, and choose appropriate scales. That means use multiples of 1, obviously 2, 5 or 10. Don't use 3, 4, 6, 7, 8 or 9. Okay, so then log values are plotted accurately gets you 1 mark. They will check that you plotted accurately, and the best line that's drawn will give you 1 mark. So if they notice that you haven't plotted accurately, you will lose the accuracy mark. So here's their graph. Okay, I'm just using their graph, and you can see all the values in the table that we just looked at are negative on both sides. So you're basically in the bottom quadrant of the graph. Okay, so that's why they put the scale of log L at the top, and then they put the scale on the right hand side. Yeah, so the positive would be up here somewhere. Yeah, so you're in a negative zone of the graph, and this seems to be a common usage of in the unit 6. So once you do that, you can see that all their points are nicely fitting on a line. They stop their lines at the 2 points. I've continued it for later because I want to know what the intercept is for an analysis section. The other thing I'd like to show is you get 1 mark for this, the labeling. You get the table's already given you 2 marks, and the scales, you see they're going up in 0.1, 0.1, 0.1, 0.1. So this is what I'm saying, multiples of 1. And here they're going up in multiples of 5. Yeah, 0.05, 0.10, 0.15. And I saw my student was going up in 4s, and he ends up going outside the last point in this graph, which is against my recommendation. The other thing I want to show you is to work out the gradient. I chose this value here and this value there to work out the delta y, if you like. Yeah, how much it's changing by. And I put everything on my graph to show that I use a large triangle, because when they're going to ask you to work out the gradient next, and I put my calculation here. Yeah, so I can show all my data, all my working. You need to do it anyway, so you might as well do it on the graph. Okay, so I hope that makes sense. That's what your graph could look like. So the next question. So we've done the graph. This is the graph paper, so we don't need to look at that. I've just shown you the examiner's graph. They then say determine the gradient of the graph. So I've shown you my graph, the graph that I used, their graph. I did the gradient on it, and see the mark scheme. So the mark scheme for this part, if I can just find the right piece of paper, they say you get 1 mark for using a large triangle to calculate the gradient, where I did use a large triangle, and your answer should be in this range. Well, I got 2 point whatever it was. They got 2.94. I tried to use the examiner's values, so when you see my answers, it matches what's in the mark scheme. Okay, and the value of the gradient can be given to 2 or 3 significant figures, and that's the 3rd mark. Okay, so that's where you get your 3 marks from. No unit, because it's just a ratio. Okay, hope that makes sense. The next part says it is suggested that for a given load L, the relationship between D and L is of this form: D equals K L to the power of R. Okay, well, if you take logs, you'll get this. You need to make sure you take logs. And this means that if you put this on the y-axis, log d on the y-axis, and you put the gradient will be r. So the gradient we've already calculated is that, and the intercept will be log k. Okay, so going back to the graph, you can see why I wanted to know where the intercept was. So you've got to make sure you leave a little bit of leeway. See, they haven't gone all the way to 0 to get all the data expanded to make their gradient better and their data more accurate. But you do need to be able to determine where it hits the y-axis. Remember, this is the y-axis going downwards, and this is the x-axis going in a negative direction. Okay, so once you've got this intercept, you can read off this value and then determine what k will be from its log. Okay, so that's useful. So if you do that, so you can get this from the graph. So log k is the c-intercept. Well, I made it 1.730 from their graph, and therefore k, that means that k is 10 to the power of minus 1.73. Okay, that's a point there. Okay, so you take, and this is taking anti-logs, it gives you a value of k of 0.0186, and the gradient we already knew from here was 2.94, so we know r is already 2.94, so they want you to determine the value k from the graph. So that's really easy if you use the intercept method, and then it means that d equals k, which is 0.0186, times L to the power of 2.94. Okay, so this is what they want you to do. One for that, one for this, and one for the in-between bit. Okay, that gets you your 15 marks. We're now on the final question, which is an oscillation question. The oscillation is by adding small lead spheres to a test tube inside a liquid. The test tube, the student placed the test tube in a small beaker of water. The test tube floated as shown. Yeah, the student gave the test tube a small vertical displacement. So vertical means up and down. The test tube then oscillated vertically. The student measured the time period of the oscillations using a stopwatch, which has a precision of 0.01 seconds usually. She repeated the measurement and calculated the mean. That means she's only measuring one oscillation, it assumes. Describe two other techniques she could use to determine t. Well, if it's going up and down in water, we don't know how often it's going to oscillate. So the normal method for measuring oscillations is to measure multiple oscillations. So for a normal pendulum in air, I would do 20. For this, they've done 5, so I'm giving their example of 5. Then divide by that number. So in this case, it will be divided by 5. 1 mark for saying that. You could also say allow, and this is a common thing on the mark schemes in this unit, allow oscillations to settle before you start timing. So you don't have to try to start it oscillating while you're starting the stopwatch. So you do it to make sure it's settled, and then when you're ready, you start timing. And then the other way they want you to know what this is, use a marker to point where it's come to the top of the oscillation or the center of the oscillation. You use a marker on the beaker. This is called it's a fiducial marker. Okay, so if English is not your first language, you could say use a marker, and they like the marker to be placed in the center of the oscillation usually. Yeah. I prefer it to be at the extreme of the oscillation. I'm just telling you what this exam board likes. Okay. She then recorded the data for the 5 T's. Yeah. And she got 4 sets of data. This is the minimum and this is the maximum. Why am I showing you that? Because you need to know the range of data, because what they're asking for is, can you calculate the mean value of T? Well, they got 5T. And it's uncertainty in seconds. And uncertainty is to do with the range of data that you've got. These all 4 add up to 13.56, but that's for 5 oscillations, so divide 13.56 by 5 would be the average for the value for 1. But of course there are 4s, you've got to also divide by 4, so the average would be 13.5 divided by 4. For 5 oscillations, divide by 5, get for 1, and it comes to 0.678. Now, you need to round that up. Why? Well, the instrument is, the precision of your timer is only 0.01 seconds, so it's meaningless to go beyond it. It is possible to go beyond it, but you'll see in a minute. why you shouldn't. The uncertainty then is half of the range of this data, which is the maximum minus the minimum, divided by 5, because there's 5 of them, and half the range will then be again divided by 2. So what's the difference? Divided by 2. So remember, this is 5, so you've got to divide by 5 because it's 5 oscillations, divided by 2 because percentage, the uncertainty is half the range. So you'll see that that gives an uncertainty of 0.021 seconds. That means we're uncertain by more than 0.02 seconds, so this 1 is meaningless. So you just say that's approximately equal to 0.02 seconds, yeah, which means this should be the same number of decimal places here as here. So you round up to 0.68 and you round the uncertainty up to 0.02, and that will help you get the marks. Okay, so never give uncertainties to more than one significant figure. It's not normal to do that. Okay. So I had my student, he put it as 678 and kept this as 0.021, and that I don't think is as meaningful. Okay. The next question, the continuation goes to the student estimated that the diameter of the test tube was approximately 2 centimeters. Explain why vernier calipers are a suitable instrument to measure that diameter. Your answer should include a calculation. So they're telling you, in other words, hint, work out what the percentage uncertainty will be with vernier calipers. Now, vernier calipers is not digital calipers, and vernier calipers use a vernier scale, and you need to know how to read them. If you haven't, go and look it up. Vernier calipers have a resolution of 0.1 millimeters. Remember, micrometers have 0.01, and digital calipers, on the other hand, also have a resolution of 0.01, but here they specifically mentioned vernier calipers. So the uncertainty would be half the resolution. So the resolution is 0.1 millimeter, half the resolution will be 0.05 millimeters. So the percentage uncertainty of using vernier calipers for a 20 millimeter, which is 2 centimeters, will be half the resolution, 0.05, divided by 20, multiplied by 100, gives you 0.25% uncertainty, which is very low, so a suitable instrument. That's how I put it. Part C, coming to the end of the paper. The student replaced the water with different liquid and determined the new value of T. T is given by this formula, or so they tell us, where D is the diameter of the test tube. That was 2 centimeters, roughly. M is the mass of the test tube and the lead spheres inside it, and rho is the density of the liquid that is being used. Okay, so we're going to use that equation in the next part to do the analysis. They want you to show that the density of the liquid must be about 1200 kilograms per meter cubed. So in other words, they want you to use the equation that's given on the previous page, and if I get rid of the square root, T squared becomes 16m over D squared rho G. Now G is gravity, density is what we want to work out. So I've changed the subject to the formula. We know everything else. So the density would be 16 pi times m, the mass of the loaded test tube, D squared, which is given here in centimeters, T squared, which is given in seconds, so you've got to change this to meters, and G, which is 9.81 in SI units. You'll notice mass is given without an uncertainty, so we can assume that the uncertainty of the mass is 0 for the purpose of this equation. So in this case, when you put all the numbers in, 48.95 times 10 to the minus 3, because that's in grams, so don't forget, don't get fooled by that. I've still got students in year 13 who forget to change it to the correct units for calculations, which is the SI unit. And then divided by D squared, 2.38 times 10 to the minus 2, to go from centimeters to meter. Square it, seconds, don't need anything, just need squaring. 9.8, you come to 1190, which is close to the 1200 that they're asking for. And then it says, show that the percentage uncertainty of this is about 4%. Well, this has no uncertainty. We've just said the mass has no uncertainty, and we're assuming that the gravity can be counted as 0 uncertainty. At least the question assumes you're going to do that. Okay, so the uncertainties come from these values. Both these values are squared. So to work out the total percentage uncertainty of rho, and none of it comes from these things because these are known accurately, okay, it comes from these values. So percentage uncertainty of rho comes from 2 times percentage uncertainty of D, because it's D squared in the equation. So each D brings its own percentage, so you're doubling the percentage uncertainty of D. You do the same for the T value, it's twice the percentage uncertainty of T. So for T, it's 0.01 out of 61 centiseconds, 0.61 seconds. So it gives you that value. That brings you a total for this part of the uncertainty calculation as 3.28% comes from the value of t, and only 0.84% comes from the same calculation for the value of d, 0.01 divided by 2.38. And this time you can keep them in centimeters because both of them in centimeters doesn't matter as long as your units are consistent. So you get the two, you add them up, comes to 4.12%, which is roughly 4%. So normally with uncertainties, we normally only use one significant figure. Okay, because even the uncertainty is uncertain. It's just an approximation of how much we get. So then the final part of the exam, the 50 marks here, we've got 2 marks left to do. The density of glycerol is given as 1260 kilograms per meter cubed. Could the value that we just calculated up there, which was 1190, be glycerol? Well, 1190 is not 1260, but we're 4% uncertain. So even if you use 4.12% uncertainty, 1190, which is the value we calculated above, plus 4.12%, which is the biggest thing, the maximum value of that would be 1190 plus 4.12%, or 1190 times 1.0412, which gives you a value on your calculator of 1,239 kilograms per meter cubed. You can still see that's still lower than this value. So since 1213, which is the maximum value with the maximum percentage uncertainty to the upside, so giving the maximum range value at the top end, it's still less than the value of glycerol. So based on this data, so glycerol's density is still higher than the maximum value calculated. So liquid is unlikely to be glycerol or not glycerol based on this calculation. And there ends this run through of the June 2023 paper. I hope you found that useful as a final practice. And if you look in the playlist on the channel for Unit 6, you'll see, I think there are already at least 3 other videos, including the January 2024 video in there. So please, if you found this useful, like it, share it with any friends who are doing the exam next week, and let's get those numbers up of the viewers to get everyone as high a grade as possible on Monday. So please like, share and subscribe, and come back for more next term. I might do some introductory videos as well over the summer to the content of the linear course rather than the modular course. Okay, well that ends my run through, and if you have any questions you can write them in the comments. Bye for now. See you in a future video hopefully. Thank you for your support.